我先去办一下我这个电脑的事情，到时候就等着你发给我那个视频了，好吧
？Okay.
Thank you.
Thank you. Oh. It's already 10 o'clock. Are there any professors going to come, or I just start? Yeah. Wait for one. What if there's no professors come, so we can just go back? We are thinking that we should wait for at least one professor. Yunxiang said that he's going to repair his computer, so he's not here for the meeting. Yeah, his computer is broken, so he needs to.
Do we know how Yijo is going to join?
No idea.
That idea, like she made it, right? You don't know.
But I have no idea.
Let me contact, because if she would like to. I would like to make sure if she wants to join instead, she can. Let me text her.
Okay. Okay, so today I'm going to present the topic of influence maximization on social graphs. It's a quite well-studied topic on viral marketing, but I'm not sure if you guys familiar with this topic, so I will start with some basic idea of influence maximization, and then continue with some recent state-of-the-art work of this topic. So this is the structure of my presentation. First, I will start with the background and some introduction of how influence maximization works, and then I choose one topic from CIKN 16 that is a broader optimization objective of the extension of influence maximization. So first, let's start with the idea of influence maximization is that it is presents how the social network and the influence spread on the graphs. So this is a very important idea of how the transitions of the opinions and ideas, informations among our social graphs. And it is well studied in direct marketing because it takes the idea of word of mouth effect. For example, like Gmail, it will at the beginning of the Gmail develops, and they ask the users to recommend other users, and then it rapidly spread the number of users of this service. So the problem setting is that it gives a limit budget of the initial advertising. For example, we have a limit budget of free samples of a product, and we want to have the maximum influence of the seed users with this initial advertising, and we want to estimate the influence between individuals. If we can try to convince a subset of individuals to adopt this new product, we want to trigger a large cascade of influence. So the question is that which set of individuals should the target budget B seeds at? For example, which blogs should be one read to be most up to date? So there are some applications besides this product marketing, like detect stories in blogs and spread of innovation, etc. Well, so what we need is that first we need to form the influence model of social network, and then obtain the data about the particular network. For example, the influence ratio between individuals, and then to devise an algorithm to maximize the spread of the influence from the seeds. So the first is how to model the influence graph. And there are two traditional influence models, that is linear threshold and independent cascade. I will introduce these two basic models later. So these two models the diffusions of influence among the graphs. So the general operation view is that this social network represents like a directed graph, and each node is the user, and each edge is the relation between them, and may have some weights that represents the influence weights. And the nodes can start with either they are active or inactive. Active means they are influenced by the product or an idea. And an active node may trigger the activation of the neighboring nodes. So I will introduce the two influence models. For the first linear threshold model is that for each node V in the graph, it has a random threshold between 0 to 1. and it has the probability to influence by each neighbor according to this weight. And then it will become active when at least the given weight fraction of the neighbors are active. I will give an example here. For example, here is a graph and with nodes, and the directed edge is the influence probability. And first, if we have the threshold of each node like this, and then first, if we have these nodes as V is active. Oh, sorry. And then it will have a ratio to have the active neighbors. And then we can find that this weight is beyond the threshold of node W, so node W is also activated. Then the influence spread, and when there's no other nodes can be activated, it stops, and we can find that the final activate nodes are 4. This is a simple example. Also, the independent cascade model has a similar idea, but it says that when node V becomes active, it has a single chance of activating each inactive neighbors with a probability P. So with the same graph, but now we don't have the threshold. We just, for example, if we start with the active node V, each time we just throw a coin and we have a probability, and we check that if this probability is larger than the influence weight among each nodes. For example, for this probability is 0.2, and it was not activated. And for the green lines, if we throw a number is larger than, at first is larger than 0.5, this node is activated. It has a successful attempt. And then also the influence will spread among the graph.
How is this different from the previous one? This also have a threshold, from what you
From the previous one is that each node has a threshold, and it checks how many neighbors is activated.
Oh, the threshold is on the number.
Yeah, the number of neighbors. And then in another independent cascade model, they don't have a threshold, they have a probability weight among each edge. So there are
But
two.
then between a pair of nodes, there should be two edges, right? On both sides, right?
This is a directed edge. So like this edge, we can see it as 2 edges with a weight of
But
0.5. If we just have,
you have no influence on the other
yeah,
direction?
yeah, it's a directed influence. So like in this case, the outer node don't have influence to you. So these are 2 basic models of,
Model is almost like the water cascading.
yeah.
So here, like once this one is activated, then this one with some probability may activate its neighbor. That is the cascade. Threshold is almost like this guy is getting everything from the upper down.
Yeah.
So here, this one gets activated if the combination of these weights are
It's
higher
above,
than is above the threshold.
Yeah. So there are 2 kinds of influence models, and they may have different methods to deal with the influence maximization problem. So then, actually, the influence maximization problem has developed over 20 years, and it was first be formulated from a paper from KDD 2003. And the paper is maximizing the spread of influence through a social network. It formulates the influence of node sets is the final output, is the expected number of active nodes at the end of the influence procedure. And if S is the initial active set. The problem is that it has a budget that is a parameter K that is a limited number of nodes as a C nodes. And they want to find that the KC nodes that will maximize the final expected number of influence nodes. And this is some properties of this F function, that it is obviously non-negative because it's the number of influence nodes. And it has two features, that is monotone and submodular. And with these two features, it can use some greedy algorithms to speed up the computation of the final results, because it would be proved that this problem is an NP-hard problem. So at first, for the submodule feature, it will let how to prove that is that first it will let N be a finite set. And then for every F with a set of S nodes and with additional nodes, it will have a larger number of influence nodes than the sets that with fewer Cs. And then it will have a function that if for every smaller set S that belongs to a larger set T, the number of the difference of the influence nodes will be larger or equal to the larger nodes. So with this submodule feature, we have some bad news that if F only takes non-negative value and is monotone, and to finding the ideal output that with K element is an NP-hard optimization problem. And for the influence maximization that apply on the both models, and it could take a long time to find the final results. But like I say, with these features, and most of the worlds apply greedy algorithms to have approximate results. And they can start with an NP set S, and for K iterations to find an approximate solution that is 1 minus 1 of E approximation. And I don't have the proof procedures here. You can refer to the paper in 2003 KDB. So then how to solve the problem? First, you have two procedures. First is to prove the performance bound, and then to compute the objective function. First is to prove that it has the submodularity feature. Like we mentioned, that if it has two we have a subset S belongs to T, and we need to prove that if S have with one additional nodes, and the final result will be a larger number with T with additional node. I will skip this proof. And so with this fixed graph, for example, we have a green graph, and that G graph is the whole graph. And we have two subsets S, and S is the red part. and T is the larger part, is the superset of S. We need to check that if we add one additional nodes, and we will have a larger number of difference between S minus the additional node than T minus the additional node V. So then the function is that the summation of the probability G plus the output of S. So this is the example of the linear cascade. Oh. And then we have a similar proof of linear threshold. So once the graph is fixed, so we can have the reachability of all the graphs from, oh, I don't have a, so we can have a similar example here. So although so this case cannot be used in linear cascade. Sorry, I will skip the proof of linear threshold. So let me continue with the how to compute the objective function. It's the second part. So we need to evaluate the final influence nodes of the C node S. How to evaluate it is from. So with our greedy algorithm, how to compute it efficiently? We need to have a good estimate by simulation. So we have start from a repeating of the diffusion process. So as a result, it will generalize a proof that shows it. I skipped too many parts. Shows that because the approximate was 1 minus 1 of E, and if we have a additional sorry, I think I skipped too many parts, so I cannot explain what's this parameter here. So with these two steps, so there are many extensive related works with the influence maximization. So with the basic idea of influence maximization problem, it will deal with some models that has discrete or continuous time models, or the hardness or greedy approximation. And also, how to improve the efficiency and scalability is an important issue because it may use some heuristic that ranks or scores before build the index that ranks and scores before the building the influence model. Also, it will use some sketch or reverse influence sampling index. Also, it has some applications that use the context-aware influence maximization. For example, the nodes contains a topic or some time constraint. Also, like it will map this graph to a map. So we'll have a location-based social network. And the paper I'm going to introduce is also a location-aware related work. Also, it may have to deal with a dynamic influence. So the influence is not fixed on the graph. So there are also other optimization objects that is business oriented that consider the marketing plans related to the graph. And then I'm going to introduce one state-of-the-art paper that is related to influence manipulation on location-based social network. And the idea is that also we have a social graph on this map. So also the nodes are users with locations. But we have additional information that is blue pin here, that is an event at a location. So in this example, we may have an event and we want to have the maximum users that will attend this event. Also, we will have some limit budget of C users. We want to become the initial user that to spread this event information. But in the real world case, we may have some constraints that is time constraint. We may not have, like this event will open in 3 days, so we will not wait for like 1 week or 1 month for the influence spread to some target users. And also we'll have a geographical region, like the red cycle here. So we have an assumption that if the users outside this region, they may not have the intention to go to this event. So in this model, they have additional 2 constraints that will make the exist solutions cannot apply on the problem. Yeah.
So what is the goal?
The goal is also maximize the influence nodes. But yeah, but in this case, they have 2 constraints. That the first constraint is that they have a time limit, because in in the original case, they don't have a time constraint. They have the influence spread until it stops. They have no chance to spread the influence. But if we have a time constraint, for example, if we assume that for each link, it takes 1 time unit to spread the influence, and we have a time constraint of 3. So like U2 cannot influence U14 because it has 4 links.
Why is the time constraint specified by that? Because typically, I mean, in reality, the time constraint could be like, well, maybe I have some event I want to broadcast, right?
Yeah.
And then, of course, my time constraint, maybe that event will happen 3 days later.
Yeah.
So my time constraint would be 3 days.
Yeah.
Because otherwise, if it's past that day, that time, right, it would be useless, right?
Yeah.
I don't care, right? I want to maximize whatever before that event.
Yeah.
Then, typically that time is way more than whatever the time needed for one person to spread the news to the next person, right? So basically, wouldn't it be like I tell John tell, like, just 3 hops and then maximally then that's done, right? So I think it will be longer than that, typically the time, I mean, in reality, the time constraint. Unless it's something really, you want is really instant influence, like real time, so almost real time. Because I don't know why they said, I know setting up this way probably easy to compute. But what other reasons setting the time constraint that way?
I think it's just applied to the case that it has an instant.
But then the geographical region constraint is also like
The range.
defined in terms of how many hops or.
Yeah, how many hops?
But then this time constraint, the geographical region
Geographical constraint is not the. It's not the how many hops. It's just because it's a location-based network.
So
So
they just
they have the location like coordinates.
I don't understand the geographical region constraints. What does it mean?
It means that they have the assumption that, for example, there's an event occurs in this location, and maybe there's and maybe this event occurs in America, and there's another user that may be social connected to the users in this area, but this user is located in Europe, and maybe this user will have a lower intention to attend this event.
But
They have assumption that the distance have a influence on the influence spread.
So the geographical region, I think we can use it in two different ways. One is somehow adding more structure to the network,
Yeah.
meaning that, let's say from user number 6 and user number 3, because they're in the same location, it's more likely that the information about that particular location that is broadcast by user number 6 might be influencing user number 3 much more than, let's say, the user number 6 is influencing, let's say, some other user who is not in the same location. So we can somehow add additional constraint on the structure of the network using that kind of information. So that is one way of using it. Another way of using it is when we have to try to optimize for things, we can try to set our goals such that we don't really care how many nodes this particular information is broadcast. We might care only among the users within that particular location who are interested in that particular location. So there are two separate ways of kind of using that high-level intuition. One is adding more structure to the network. The other one is somehow changing our goal function, optimization function. When I say I don't understand it, I don't understand how you're using it.
Yeah, I think in this case, in this paper, it's applied to the second case.
Which is we only care about
Only
those
care
terms
about
within
the
a particular geographic region.
the target users are constrained in the geographical region.
How do they know the provenance of the user is the average node?
Sorry, how do
how
they?
do you know the location of each user?
In this paper, they just use the most frequent locations of each of these users. For example, user 1 always check in at UCLA, so it will locate. This user will locate in UCLA.
It must be there's some resolution because typically it's not the same.
Yeah, it's not.
Exactly the same location, right? So
I think they in the experiment they simplify this, but actually this model, every user will have a parameter that is their location, and if they have other methods to find out this location, it can apply to this algorithm. I think, but actually, yeah, it's simplified many informations. So actually, the solution of this paper is that they build an index that considers the two constraints and then can apply to the greedy algorithms. So should I continue? And because they have, it's a location-based social network, so they have two influence cases. The first is the traditional influence that the user's neighbors have propagated information of an event to him or her. And they have another definition that a user is registered if he or she is influenced and then decided to participate in that event. So they will, like in this location-based social network, they will have a check-in record.
So when you say neighbor, is it geographical neighbor or is just the other user have a connection with?
The neighbor is the connection.
Right, so it doesn't have to be in that region.
No,
right?
don't have to be in that region. So the neighbor is the neighbors on the network. Okay.
Very high level question. So right now you're trying to tell us
Yeah. With this, because they want to solve the previous problem, and then I will use these preliminaries to formulate, to define the problem they propose. That is a target influence maximization problem. Because traditional influence maximization problem is to influence the largest number of users on the online network. But this paper, they want to solve the problem that is to find out the C users that will have the most registered participants in the constraint area. Also, they have a time constraint. That is the.
That result in most registers. So means they send out the message.
They still have a set of KC users, and as the initial seeds, they will send out information that propagate the social network. But the final result is that they want to have the most influence users that will like check in that region.
Okay. This K user doesn't have to be in that region, right? It can be any.
They don't need to be in that region. But usually, they will be in the region because the users in the specific region will influence more. Not necessarily. So in the.
What is the border between influence and registration? So do we assume that as long as a particular user is in the same region or same location, and that is within the same time horizon, then whenever the user is influenced, the user will immediately register? Is that the assumption?
No. Because we have the definition here, the influence, we have the assumption that they will like receive the informations.
Right. So
And then
the traditional definition of activation.
yeah.
And
then register means that they not only receive the information, and then they receive the event information and then participate
so
and
my question
go
is,
to that.
My question is, what's the model to convert an influence to a registration? When does the user decide to register? When the user is influenced?
Oh, then because we have these two definitions, so in the generation of the social graph, we'll have another function that is a login function. It's the probability that the user being influenced and then have the intention to register in that location. So we have additional probability, like for example, in this case, if we use the cascade model, and each link will have a probability of the influence, and then for each node, it will have a login, like a threshold. That means that if this node is influenced, and then if it has another probability that among the login value threshold, it will participate in that event. So we have we have two additional thresholds.
So like this registration probability function, what's the input? What's the input parameter of that function?
The input parameter is the time. It's the time constraint and region constraint, and KC nodes. We have a limit number of seed nodes. So it's the number of initial activate users.
No. So here is my question. So I just got, like, I'm following various users.
Yeah.
From one of the users, I heard about that event.
Yeah.
Now, I have to make a decision. Do I want to register or do I want to not register?
Oh.
How do I make the decision?
This is the process of building this network. But in this case, these informations are all predefined. So like the definitions here. So each node here, will associate with the location. And like I say, the location might be the most frequent location or any location you to extract the local location. And then each node has a login probability. This login probability means that represents that the probability that if the user is influenced, and then the user will have the login probability to participate in the event.
I see. So here, my probability of registering is purely a function of that
Yeah.
probability. And that login probability is independent of the node, or every node has the same value?
It's independent. Every node has an independent login
Every
value.
node has their own unique value.
Yeah.
Login probability.
Yeah, but it's generated by the input network. So in
How do we know the login probability?
actually, it will be another research topic that how to build this network for some depending on different input data. But in this paper, they have predefined network.
And then that login probability is not a function of the influence threshold or influence
No,
value.
it's
just
another.
a single value that is associated with it.
Yeah.
So then whether or not a user like me would register or not, just based on that login probability?
Because we have two kinds of influence. The first influence is the influence on the network, and the second influence is if you are influenced, you receive the information, and what's the chance, what's the probability you are going to attend that event.
So as long as I receive one such message, I'm going to apply that login probability.
Yeah.
It doesn't matter whom I receive this message.
Doesn't matter because after you receive this message, you are in this graph you are activate. So it doesn't matter that whom you receive.
But if this message was from
Oh.
John.
John,
You will register.
I will register. And then if this message is from Donald Trump, I will not.
Oh.
Why?
Yeah.
Why is
If this message is from because you have different probabilities between different users. If this message is from Trump, you will not be activated. You will not influenced by that message.
Okay. Well, sometimes it also depends on the content of the message.
True.
Right? Even if this message is from Trump, let's say, and if the message is about register for whatever, right? some political issues, then I wouldn't care. If this message is for say, please register so that we can maybe support
Research.
research, for NSF or something, right? So then I probably would. Let's see that this is important. I want to register, right? So it depends on the thing.
Yes.
The subject, not just the person who sent me.
Yes. So in this network, maybe it's too simplified, but like there are other related works that they will have a dynamic influence. So the probability might change, varies among different topics. But in this network, it's fixed. The influence probability is fixed. So the only input they have is besides this model is a deadline, a time constraint, and then event location. And the output is the same as a influence maximization problem that is a set of k users, but maximize the expected number of registered users that the user will participate in the event location.
So another question, assume that this is the person receives the message would also pass the message along to the next node,
Yeah.
right? So in that case, does the user need to register him or herself, and then these
Nope.
two independent?
Nope. It's independent.
Then what's the probability of I receive a message and then send it out, pass it to other my neighbors? What's the probability of that?
So it depends on the model, because like in the original independent cascade model, you receive a message and you have like if U2 receive a message from U1, and it will have a probability. If, for example, if this weight is 0.5.
Model, how is it being represented, that probability?
So it's independent that whether you influence.
Some way, right? So because here for the two variable, it doesn't say how that, what's the probability of that message being passed along to the.
How the information propagate in this network is related to the influence model and not related to the login value. But like U2 may have influence U4 and to influence to transit one information to another user, but this particular user may not attend.
I understand, but in the model, it has to be represented that in some way, right? So what's the assumption? Like, there is also an independent probability that associated with each user to pass along the information he or she receive, or there's some other model assume how the message got propagated.
Also, for every step, because the information is transported step by step. For every step, we will record the status of each node. So each node we can check that is it activate. So it's the influence and whether he or she is registered. So you have two status.
And then after that, what?
So after that, we can move to next step. And next step, we will check that if additional users are influenced and
No. Before you go to additional user influence, you have to say how the message got sent out again, right?
yeah.
But how?
So we will have the like a screenshot of this
No,
for
but
this.
I'm saying that what is that you assume or this paper assume a probability of each user, like I receive a message and then how likely I'm going to send it out, or you assume that it's always sent out, or you assume what's the
They have a probability of each age that they send out this information.
But that should be a different probability of that probability, right?
It's the
It shouldn't be the influence probability.
It's the influence probability.
Why?
Because
The probability I send out a message to you is independent of the probability that after you receive that message, whether you will be influenced or not. That's two separate probabilities.
but
It's not the same probability.
so in their definition, the probability of users sending out a message is fixed. So it has a fixed weight here that
Okay.
whether
Yeah,
you
but
are
all
active,
I need to know is how they decide how the message.
how they
message is-
decide
yeah,
the
because they have to-
probability.
Yeah, they have to decide one way or the other to say, well, how the message got propagated.
Yeah, the simplest way of how to decide the probability is the in degree number. So, for example,
The in-degree number decide how likely.
they send out the information.
Why?
For
The
example,
in-degree means that how many other people influence me, right?
yeah, how
They
many?
influence me, then how that determines
Oh,
how I'm going to
it's
send out
the
a message.
sorry, it's the out degree number. So, for example, U6 only have one link to U3, So the probability that U6 influence U3 is 1. So it's out degree. Yeah, it's quite.
That's different from the probability that one U6 will decide to send out a message. That shouldn't be dependent on.
Yeah, it's one way to define the weights, but it can be depend on other informations you have. If, for example, we have other.
But how is it defined in this paper? That's what I'm asking.
In this paper, because they did not explain how they generate this network, but in the experiment, yeah, in the experiment, they use the out degree to define the weights. Yeah, because they just focus on how to build the index model that records the time constraint information and location constraint information. Yeah.
That's the easy part. Time and location.
Yeah. So it's actually the method is quite easy. That they build random sampling sets at first, because they want to apply a greedy selection process that can maximum coverage the nodes that will be influenced. And the idea of random sampling nodes is from another ICSIS paper. Then I will explain what the index model they built in the following page. And then with this index model that is a weighted random sampling graph, they will apply the greedy algorithm, that is the target influence maximization, to select the weighted random sampling tree to find out the influence nodes. And then with the iterations, they will got the final results. So how to, first, with the initial network, they want to build a weighted reverse reachable tree. Is the index model first. So like in this example, for each node, it's a independent cascade model. So for each node, they have a probability of influence. And then the underlying value is the log-in probability. Then it will randomly build a set of graph instance from this original network. For example, it has, for each link, for each edge, they have a probability to select this edge. And then it will build several graph instances. Then, because for each node, they will have a graph instance, and then you use graph depth search. Breadth first search to build a weighted reachable tree that can find out the most influenced users of these nodes, root nodes. So it is applying the probability of the reachability of nodes. For example, like these three in this case will be reached 2 times. And so it will appear 2 times here. And then with these WRR trees, they will apply the greedy selection. So for each greedy iteration, they will have to randomly select a user U that with the highest probability of the registering login values, and then to set the weight of each node to copy the influence values. And then for each iteration, it computes the weight of different subsets. Then the final returning set S will be the approximate C nodes. And how they do the experiments to evaluate their results, they use 4 location-based social networks, and how to set the experiment conditions that for each round, they say the random target location, and in their experiment, the time limit is 10 days. And then evaluate because you can, in the real world case, you can find out the real registered users as a result that they visit this random target location. And then this target influence maximization problem, it compares to other state-of-the-art influence maximization methods. For example, expansion exists work but cannot consider the time constraints. And MIA is another exists method that cannot consider the location constraints. And with this experiment, it proves that the time constraint and location constraint do influence the final register users. The conclusion of this work is that it proposes an extension of influence maximization problem that can be applied in real-world applications. And then it built a weighted reverse reachable tree that can use to build an index that apply in the greedy algorithm. But like I say, the model of inference graph is quite simple. So actually, they have much future work can do that. For example, how to consider the multi-campaign influence, that the different nodes may have different influence among different topics. And different users may have user preference or event types that they are interested in. And this is one example of application in influence maximization. And recently, we still have other future directions of it, that, like in theoretical part, how to efficient approximate algorithms under specific conditions. And then for practical problem that, for example, in different networks, it's hard to build the influence probabilities. So it's true that if we have fixed probability here, is not applicable for real world. So how to build this input model is also an important issue. So this is the last page of my presentation.
So why did you pick this paper?
I picked this topic because my recent research is about marketing, and I choose this paper is that because that I have a work that is related to influence maximization in location-based social network, but our problem definition is not. It's different.
So, in your opinion, what's the biggest contribution
So I think the contribution of this paper is that they have a applied condition that considers the time constraints and location constraint, but it's true that the problem definition is too simplified.
Yeah. So, which year was this paper published?
2 years ago.
2 years.
But I've checked that there is
so
no.
there's nobody
Mm,
to make the assumption more realistic.
I have checked some works in 2007, but I did not find out. But maybe there is some in this year. I'm not sure.
Any
Can you go back to the
Which page?
evaluation slide, the curve, the 4 figures?
This one?
Yes. So they randomly select a location as the event location, right?
Yeah.
And finally, they conclude some method that they can, for this event, more than 20K users will check in at that business.
This K is the number of initial seats.
Oh.
So, like in this koala case, if the
Allowed users will actually check in.
allowed number,
For example, the bigger one, the Java, for example, there may be 500 users finally checking at that.
you mean the ratio of the
On the right is the number of registered users, right?
yeah
I'm very surprised with so many users that have check-in.
checking at that
Yeah,
location.
Yeah, because usually I know on average maybe only less than 10
Yeah,
check in particular business.
I think, in my opinion, I think they choose the locations that will have a lot of users will check in, but.
What they said, right?
Yeah.
They
Yeah, they say that random, but yes, it's true that the registered user number is so large.
Maybe they are cheap.
Who are the authors? Who are the authors?
The authors is in the first page. I forgot to list the affiliations they from.
Is it from Singapore?
Maybe. Let me check. Yeah, they are from Singapore. National University of Singapore.
Yeah, it's in my classifier names. Okay.
Okay.
Yeah, I'm just curious. Any other questions? Okay, thank you.
Thank you.